Hey guys, Mr. Smith here, starting off Unit 2, and today we're shooting a lesson on something called the Remainder Theorem. So let's get started. So in this unit, we're still working with polynomials, but this time we're more focused on polynomial equations. In your grade 10 course, you guys actually have some experience with polynomial equations, specifically quadratic equations. And in your grade 10 course, you guys learned how to solve quadratic equations by factoring. So I've got a quick example here where you have the quadratic equation x squared plus 4x minus 5, which can be factored into x plus 5 times x minus 1. I don't like red. Yeah, so we factor, and then you guys learn that, okay, we either the first factor, x plus 5, is equal to 0, right? And that gives you x equals minus 5. Or that second factor is 0, and that gave you x equals 1. In the same way, we'd like to take polynomial equations like this quartic equation and factor it and solve equations like that by factoring. So in this unit, we're going to develop some skills to help us solve or factor equations like this. And so our starting point is going to be long division. And if you thought you were done long division after grade 3, you were mistaken. Long division is going to help us out over the next while, and we're actually learn how to divide a polynomial by a binomial. But as a bit of motivation, we're going to just do some long division with just plain old numbers, just like you guys are back in grade 3. So I have a long division here, and we'll walk through the process for long division. So how many times does 17 go into 357? Well, first of all, maybe we'll talk about some notation. In a division, we call what we're dividing by, we call that the divisor. So in this question here, 17 is a divisor. We call what is underneath the division sign here, this is the dividend. And when we get our answer, that's going to be what we call the quotient. So let's actually do this. So way back in grade 3, you'd have been taught, okay, so we take 17 and we see how many times it goes into, well, you start with 3, and 17 doesn't go into 3 any times. Then you look at the next digit. How many times does 17 go into 35? 17 goes into 35 twice. You put a 2 above the 5, and then you multiply. 2 times 17 is 34, and then you subtract. 35 minus 34 is 1. And then you bring down the 7, and then you repeat the process. How many times does 17 go into 17? 1 time. And then it's a bit of a check. You do 1 times 17, you get 17, and you subtract, you get 0. 21 is the quotient, and here we have a remainder of 0. And of course, what this is telling us, this long division, is that 357 is equal to 17 times 21, essentially what we found out. What we did here with numbers, we can apply this method to polynomials as well. So I want to show you guys how we can do that in our next example. So here we're dividing x squared plus 9x plus 20 by x plus 4. And the answer we get should not surprise you, but let's dive in. So again, just for this particular one, we'll just label the terms here. So x plus 4 would be our divisor. The trinomial x squared plus 9x plus 20 is our dividend. And whatever we get on top as our result will be the quotient. So how do we apply this method to polynomials and binomials? What we do is we look at the leading term. We ask ourselves, how many times does x go into x squared? Well, it goes in x times, right? X times x is x squared. And then we multiply. It's just the same process. X times x, x squared, x times 4, 4x. And then we subtract. So if you want to show the subtraction, I'll just put it in brackets here. X squared minus x squared is 0. And 9x, and that will always happen. That leading term will go to 0. 9x minus 4x is 5x. And then you bring down the plus 20. And then you repeat the process. Look at the leading terms. You ask how many times does x go into 5x? 5 times plus 5. 5 times x plus 4 is 5x plus 20. And then you subtract. And in this case, we get 0. Now, this shouldn't come as a surprise to you guys because we already knew that x squared plus 9x plus 20 could already be factored as x plus 4 times x plus 7. We just observed that result using long division. The big idea, guys, though, is that we can divide polynomials by binomials using the same method as we did when we were in grade school. Now, admittedly, it takes a bit of practice. So in this lesson, we're going to be doing a lot of long divisions and hopefully just improving the skill and becoming proficient at it. So there will be a lot of long divisions and a lot of, on your end, possibly pausing the lesson video, trying a long division, and then coming back. But I have 2 more for you guys. And again, you can, at any time, feel free to pause the video and come back when you want to check an answer or something. Let's do this one. So 22. How many times does it go into 7? None. So we don't start there. Let's go 22 into 75. It goes in 3 times. And 3 times 22 is 66. We subtract. 75 minus 66 is 9. And then we bring down the 3. 22 doesn't perfectly go into 93, but it goes in 4 times. 4 times 22 is 88. 93 minus 88 is 5. In this case, you can see we have a remainder. And what we get is if we wanted to write a statement like we did before, we could say this: that 73 is equal to 22 times 34, but not perfectly. You've got this remainder of 5 plus 5, right? You've got our dividend. 22 was our divisor. 34 was our quotient. But in this case, because the division didn't work out perfectly, we have a remainder that was not 0. In this case, the remainder was 5. In the same way, you can get remainders when you do polynomial division. So let's look at another example, dividing a polynomial by a binomial. Now, if you look at x squared plus 5x plus 7, and you think about trying to factor that, you would see, okay, that can't be factored over the integers, can't be factored. So x plus 2 does not go in perfectly. Let's see what happens, and then we'll write out a similar statement like we did before. So again, we look at the leading terms. X goes into x squared x times, and then you multiply. X squared plus 2x. You subtract. If you want to show, do like that. X squared minus x squared is 0. 5x minus 2x is 3x. You always, always, always end up with that leading term subtracting to 0. And then we bring down plus 7 and repeat the process. X goes into 3x 3 times. 3 times x plus 2 is 3x plus 6. And when we subtract these guys, we get a remainder of 1. And that's okay. Our result can be shown this way. X squared plus 5x plus 7 is equal to x plus 2 times x plus 3, but not quite. We have this remainder of 1. And you can verify that if you wanted to by expanding and simplifying. And we will check some of these later. But again, guys, this is long division by polynomials. It's the skill we want to develop today and also make some new connections. So let's continue. So yeah, at this point, hopefully you're convinced that the same terminology and method we use to divide numbers, we can do that with polynomials dividing by a binomial. And we mentioned that in B, the remainder was 0. That's because x plus 4 was actually a factor of x squared plus 9 plus 20. However, in D, because x plus 2 was not a factor of x squared plus 5x plus 7, we got a remainder of 1. All right, we're going to start the process of motivating connections between the remainder and the factors we're dividing by. But let's just try and get a bit better with the long division. Let's try a bigger polynomial division now. All right, so in this question, we're going to divide the cubic polynomial, minus 3x squared plus 2x cubed plus 8x minus 12 by x minus 1. So let's set up our long division. And then there's one talking point with this guy here. X minus 1, big division sign. Now, it's very important when you're doing long division to put the terms in order from highest to lowest. The original expression here was not. It had the squared term first. We want to put these terms in descending order. So I'll just add a little note here, descending order. That's very important to apply this method. All right. And now we can begin. So we look at, again, maybe I'll switch to green, switch to a different color for my solution. That might be helpful here. So look at the leading terms. X goes into 2x cubed, 2x squared times. 2x squared times x is 2x cubed, and 2x squared times negative 1, negative 2x squared. Okay, now subtract. We have to be careful. We're subtracting two polynomials here. 2x cubed minus 2x cubed is 0. Negative 3x squared subtract negative 2x squared is negative 1x squared. Bring down the 8x. And now we repeat the process. Leading terms. X goes into negative x squared, negative x times. Self-check when you multiply it out. These terms should match up. And negative x times negative 1, positive 1x. I now subtract. Negative x squared subtract itself is 0. And 8x subtract 1x, 7x. We finally bring down minus 12 and repeat the process one more time. X goes into 7x 7 times. 7 times x minus 1 is 7x minus 7. And when you subtract, negative 12 subtract negative 7 is negative 5. And we've got it, guys. I'm going to, for most of our problems, I'm going to continue to kind of write out this expression we can use to check our answer. What we have just shown is that 2x cubed minus 3x squared plus 8x minus 12 is equal to x minus 1 times 2x squared minus x plus 7 with a remainder of minus 5. And again, we like writing these statements, at least initially with our long divisions, because it allows us to check our answer. And we definitely will do some checks. One other way to write this as well, I might show you guys in a different color here. You could write this as the following, or you could say this. The result when you do 2x cubed minus 3x squared plus 8x minus 12, when you divide that by x minus 1, just fix that up. When you divide by x minus 1, the result is 2x squared minus x plus 7 minus this little remainder, 5 all over x minus 1. You get that statement just by dividing the previous one. Me personally, I prefer writing statements out like this to help me check and visualize. I personally don't find statements like this too helpful as far as checking goes, but these kind of statements can be helpful later on in our course when we start to talk about asymptotes and drawing some rational functions. But that's for another time. So for today, guys, most of my statements will be in the first form in green there. One thing I want to mention too, the statement I wrote in green there works for all values except 1. You guys have heard time and time again that you can't divide by 0. And there's actually a value of x here that gives us a problem. It makes it so that we're dividing by 0. And the problem here is 1. So we do have one restriction on our, so I'm just going to add a little note here. We have a restriction for x. We do have one restriction that x cannot be equal to 1. Because in that case, we'd be dividing by 0. And of course, only Chuck Norris can divide by 0. We can't divide by 0 in this course. All right, so that was a bit of a longer polynomial division. So hopefully you guys are kind of getting the hang of it at this point. We got lots of practice in this note. Don't worry though, lots of practice. Okay, so what you guys have seen is that when you divide one polynomial by a binomial, what you get is actually another polynomial that has one less degree, right? We divided this dividend, this cubic polynomial, by a linear polynomial, x minus 1, and we wound up getting a quadratic polynomial, plus some remainder. In this case, it was negative 5 over our divisor. So that's what this statement, the first statement, is saying. When you divide a polynomial, p of x, by a binomial of the form x minus b, you get another function, q of x, and then some remainder. Now, the corresponding statement for me is more useful. When we divide the function p at x by x minus b, we get a function q at x plus some remainder. I personally find that more helpful, but again, both of these statements can be helpful at different times. For our purposes today, I'll be writing a lot of these corresponding statements like we have below. All right, let's continue. Here's another example. And in the previous few, our binomial had a coefficient, or a leading coefficient of 1. What happens if it's a binomial of the form ax minus b, something like that, right? Where a doesn't equal 1. Well, let's have a look. You know what? I got purple in here. Let's work with purple. So we're dividing 2x plus 1 into this cubic polynomial, 4x cubed. Now, this is an important point, guys. You'll notice that this expression does not have a squared term. For our algorithm to work of long division, we need to fill in a placeholder, 0x squared plus 9x minus 12. So we call that a placeholder. Very, very important. So not only do the terms need to be in descending order of degree, sometimes you're going to need a placeholder when there's no, in this case, say quadratic term. But now we can proceed like we normally do. Look at the leading terms, 2x and 4x cubed. I'm going to switch back to dark green just for a bit of contrast here. 2x goes into 4x cubed, 2x squared times. Multiply. This self-check always works. These always are the same. And then 2x squared times 1 plus 2x squared. And then we subtract. We get negative 2x squared. And we bring down the 9x plus 9x. All right, and then we let's keep it going. Look at the leading terms: 2x and negative 2x squared. 2x goes into negative 2x squared. Negative 1x times. Multiply it out. Negative 2x squared. Negative x times 1 is negative x. We subtract and are careful with the negatives. 9 take away negative 1 is positive 10. And we're almost done. 2x goes into 10x exactly 5 times. 5 times 2x, 10x. 5 times 1 plus 5. And finally subtract. Negative 12 take away 5 is negative 17. All right, so what we have here, we can write this statement that we can use to check the division. And you know what? Just for fun, guys, let's actually check this one. I'm going to call a bit of an audible here and check this one out. So what we have shown is that 4x cubed, this is our statement to check, plus 9x minus 12 is equal to 2x plus 1 times 2x squared minus x plus 5 minus 17. But let's actually check this one out. So to check, we have to use the distributive law. We're going to multiply 2x by everything in here. That's 6 multiplications. So we get 4x cubed minus 2x squared plus 10x. And then we'll multiply 1 by everything. 1 by everything in here. Plus 2x squared minus x plus 5 minus 17. And then we'll clean things up. So we get 4x cubed, negative 2x squared, and 2x squared add to 0. 10x minus 1x is 9x. And 5 take away 17, negative 12. And so we know that we did it right. And you can always check. And, if you're just doing like homework and practice and stuff, maybe not so important. But if this was, on an evaluation, then, if you have a moment or two to spare, checking an answer like this can ensure you have it right, can give you that self-confidence, knowing you have those marks in your back pocket, and you can proceed and feel good. In this case, we do have one restriction. The restriction here is that whatever 2x plus 1 is, it can't be 0, right? Because then you'd be dividing by 0. What does this mean for x? If you solve for x in this little inequality here, moving the 1 over and dividing by 2, x can't be negative 1/2 or negative 0.5. That would be the restriction on the variable in this case. All right, so hopefully at this point, we're feeling more comfortable with long division. It's going to take some practice, and we know how to check an answer. We know how to write out a statement that allows us to check our answer. And we know how to identify restrictions on the variable x. We look at what we're dividing by, the divisor, and just say whatever makes that 0. In this case, it was minus 1/2. All right, guys, let's continue. This is a classic application problem. In this case, we have the volume of a rectangular box. We don't know specifically what the volume is. We have an expression for it. It's a cubic polynomial. And we're going to find possible dimensions for the box if the height is given by x plus 2. So we're going to be using the fact that volume equals length times width times height. And because we have the volume and the height, we're going to be dividing the volume by the height to get an expression for the product of the length and width. And you guys will see why this is helpful. But let's give it a shot. So let's do that. Let's divide x plus 2 into this cubic polynomial, x cubed plus 7x squared plus 14x plus 8. I'm going to use a different color here. And you guys know the drill, right? You don't have to listen to me drone on. If you just want to pause the video and kind of fast forward a little bit, will not be offended. Or you can just kind of follow along with me if that's what you prefer. X goes into x cubed, x squared times x cubed plus 2x squared, and then we subtract. If I had a video editor, I'd pay them to just like take out those spots where I'm erasing stuff, but I don't. 7x squared minus 2x squared, 5x squared. And then we bring down the 14x, and we continue. X goes into 5x squared, 5x times. 5x times x plus 2, 5x squared plus 10x. We subtract. We get 4x, and we bring down the 8 plus 8. X goes into 4x, exactly 4 times. And check this out. 4 times x plus 2 gives us exactly 4x plus 8 and leaves us with a remainder of 0. So what have we shown here, guys? We have shown that this volume expression, which was x cubed plus 7x squared plus 14x plus 8, is actually equal to this expression for the height, x plus 2, times x squared plus 5x plus 4. And I'm going to switch back to green to highlight a little something here. The darker green. The volume is equal to this height. Remember, volume is length times width times height. So this expression, x squared plus 5x plus 4, must be the product of the length and width. And astute observers may have seen that we can actually factor that trinomial into x plus 1 times x plus 4. So we get x plus 2 times x plus 1 times x plus 4. And now we have expressions for the length, the width, and the height. Possible expressions anyway. So the height is x plus 2, and the length and width could be x plus 1 or x plus 4. Possible dimensions for our box. All right, and interesting thing too, if you think about what we've done, we've actually factored our first cubic polynomial using long division. And maybe in your grade 11 course, you factored some cubic polynomials that you could handle by grouping. This one you can't do by grouping, so this is pretty cool, unlocking some new skills and some new ways to factor expressions. All right, let's continue. We now want to motivate something called the remainder theorem. It's kind of like the culmination of today's lesson. So what I have for you guys is 4 more long divisions. And so my hope is that you pause the video and try these yourself. I myself, just to cut down on the shooting time here, I'm going to pause as I do these and then come back with you guys with the solution. So 4 divisions for you guys to do. For the same polynomial, we're working the polynomial p of x equals 2x cubed plus 6x squared plus 2x minus 4. And you're dividing by 4 different divisors. And then you're evaluating that polynomial function by what's in the divisor. So x minus 1, you're going to be, that corresponds to a root of 1. You're going to find out what the value is when you sub that in. When you do x plus 2, you're going to plug in corresponding negative 2. When you're doing 2x minus 1, the corresponding root there is 1/2. Plug that in. And hopefully you start to make some connections. So I'm going to leave this with you guys. Give these 4 a try. See if you can make some connections. And then unpause the video and pop back in when you're ready to compare. All right, guys, so hopefully you took some time, you paused the video, and you gave these a go. And what you hopefully would have seen is that the remainder you get when doing the long division corresponds to the value of that function um, at that corresponding root. So when you divide by x minus 1, that corresponds to root of 1. You get 6 when you plug it in the function, and you get 6 when you divide by x minus 1. For the next one, when we divide it by x plus 2, that's a corresponding root of negative 2, and you get 0 as the remainder, and you get 0 when you evaluate the function at negative 2. It works for a binomial with that doesn't have a leading coefficient of 1. So this one might have been a bit tougher for you if you have problems working with fractions. Fractions they are going to happen, but yeah, I'll just maybe even talk through this one. 2x goes into 2x cubed x squared times. Multiply, you get 2x squared minus x squared, and then subtract. 6 take away negative 1 is 7x squared. You may have noticed a personal preference for me as I'm doing my work with these. I understand I'm subtracting these guys, so I don't often on my own work write in the negative sign. I don't often write in subtract this because sometimes I find that can just get things too cluttered. But if that helps you, for sure, write those in. I mean, you do you, right? Now 2x goes into 7x squared, so 2 doesn't go into 7 a whole amount of times. It goes in 3.5 times, or 7 over 2. So 7 over 2x multiplied by 2x minus 1 gives you 7x squared minus 7 over 2x. And then you just got to be careful with subtractions. 2 is like 4 over 2. Subtract negative 7 over 2. So like you add, you get 11 over 2. And 11 over 2 divided by 2 is 11 over 4. That's where that came from. And when you multiply that out, you get 11 over 2x minus 11 over 4. When you subtract negative 4, take away the negative 11 over 4. It's like adding 11 over 4. You get negative 5 over 4. It does correspond to the value of the function. So just to show you guys just that it works. And then finally, this next one, when you divide it by x minus 2, the remainder is 40. And lo and behold, when you plug in 2, you get 40 for the value of the function. So this, what you guys have verified here, is actually the remainder theorem. And we can summarize the remainder theorem in this way. When you take a polynomial and you divide by some binomial x minus b, the remainder corresponds to the value of that function at b, which is pretty cool the way that works. When you divide by ax minus b, the remainder is the value of the function at b over a. And of course, where does that b over a comes from? It comes from, what is the root of this equation? Well, it's x equals b over a. Of course, this gives a condition that a can't be 0. Otherwise, you don't have a linear term. You have a constant term. That's the remainder theorem. The remainder theorem can be very, very helpful and will be helpful to us later as we try to factor bigger polynomials, because when the remainder is 0, that means that our binomial is a factor. That's for the next lesson. What we want to do now is just do a couple more divisions, get comfortable with the remainder theorem. So before we even do a division here, we know what the resulting remainder is going to be when we divide this cubic function by x plus 1. So let's do a. We know that the remainder is going to be the value of the function at negative 1. Right? This is like x subtract negative 1. And let's just find out what that is. Negative 1 cubed plus negative 1 squared minus 3 times negative 1 minus 6. That would give us negative 2 plus 1 plus 3 minus 6. And that is negative 4, I believe. So what we're expecting when we do this long division is to see a remainder of negative 4. And yeah, let's try it. If you want to pause the video, great. If you want to follow along, great too. You guys know the drill at this point. some people just want to plow ahead and check in. Some people just want the comforting voice of a wise teacher who knows what they're doing. Well, most of the time anyway. Right, x goes into 2x cubed, 2x squared times 2x cubed plus 2x squared, and subtract negative 1x squared, bring down minus 3. X goes into negative x squared, negative x times negative x squared minus x. Careful with the subtraction. Negative 3 take away negative 1 is negative 2. X goes into negative 2x, negative 2 times, and then we get negative 2x minus 2. And would you look at that? Negative 6, subtract negative 2 is negative 4. And yeah, it works. That's pretty cool. In our next example, and we're almost done, guys. Great job. Done a lot today. We're just going to find the remainder. We're not going to verify this one by long division. But what this question is getting you to practice is like, what are you going to plug in to the function to find the remainder? And, if you can't read it right off, then just set this equal to 0 and solve, right? So what we're plugging in, we're finding the value of the function at 3 over 2. That's what we're finding. So let's evaluate. What is the value of the function at 3 over 2? So 2 times 3 over 2 cubed plus 3 over 2 squared minus 3 times 3 over 2 minus 6. Now, that does give you 1.5. It's not the end of the world if you use decimals here, but I'm just going to keep things as fractions. So 3 over 2 cubed is 27 over 8 times 2 would be 54 over 8. 3 over 2 squared is 9 over 4. 3 times 3 over 2 is minus 9 over 2 minus 6. I'm just going to make everything a fraction over 8 plus 18 over 8 minus 36 over 8 and then minus 48 over 8. Now, I might be getting myself into trouble here. Let's with the mental math. But let's try to do this. So that's 72. Take away 84. I believe that's minus 12 over 8 or minus 3 over 2. And yeah, I'm actually, just to make sure, I'm just checking my answer there. Yeah, I did that one okay. Now, if you would like to verify that with long division, then by all means, please do. But as we saw earlier, long division with these fraction roots can be a little sticky. Possible, but not very practical. I'd much rather use the remainder theorem. Okay. This is the last thing we're going to do, guys. We're going to apply our knowledge of the remainder theorem to solve this problem. So here we have a quartic polynomial, but we don't know the coefficient on the cubic term. But we are told when we divide by x minus 2, the remainder is 8. We can use the remainder theorem here. We know that if we evaluate, so if we let p of x equal 3x to the power 4 plus kx cubed minus 7x minus 10, we know because of the remainder theorem that the value of that function evaluated as 2 is going to be equal to 8. And let's actually just work this out. What is p at 2? So it's 3 times 2 to the power 4 plus k times 2 to the power 3 minus 7 times 2 minus 10, and we know that's equal to 8. And we've created an equation that we can solve for k. This is 48 plus 8k minus 14 minus 10 equals 8. You can probably do this in less steps than me, but 48 minus 24, that's plus 24 equals 8. 8k is equal to negative 16, and so k is equal to negative 2. Um, the value of our cubic coefficient is negative 2. This is also a question where you could check your answer by doing the long division, x minus 2 into 3x to the power 4 minus 2x cubed minus 7x minus 10. And if you did that long division, we would expect a remainder of 8 at the end of it. So I think we've done enough long divisions, but feel free to check if you'd like. All right, guys, great job. For a second there, I was like, oh my gosh, we have more, but no, that's it. Where are we heading next? So as we saw, sometimes the remainder is 0. And what that means is that the binomial you're dividing by is actually a factor of the polynomial. So if we can use our remainder theorem combined with long division, we can take large polynomials and factor them. And we essentially did this in our application question. We took that cubic polynomial, x cubed plus 7x squared plus 14x plus 8, and we factored it into x plus 2, x plus 1, x plus 4. So pretty exciting stuff. That's where we're going. That's what we're going for. Right now, you guys need to get comfortable doing long division. So as usual, do as much as you want to or need to with the practice. It's up to you. You guys are mature students. You guys can decide. You guys can get a feel for whether you're getting a skill or not and can practice accordingly. So feel free to do all or none or some of the suggested practice, but you need to get very comfortable doing long division and getting comfortable applying the remainder theorem. All right, guys, that's it from me. Great job with today's lesson. Hope you guys are staying well. Take care, and we'll see you soon.